All right, light is on. We have to make an effort to cover way many topics today because I really want to be done with this Sturm-Liouville type problems so we can splurge and do some interesting things next week. No, actually next week. Well, yeah, on Monday, starting on Monday. And the following week. Okay, so we don't have class on Wednesday, I believe, right? All right. So let me go, and I promised I was going to repeat the discussion on the transient nonlinear heat conduction problem. So let's spend no more than 10 minutes to do this. So this is the, all right, this is the transient heat conduction problem. So P is the conductivity, heat sources. This is, you can think of this density times specific heat, okay? And we have some generalized boundary conditions that involve both derivatives and U. So this is what, you know, it's like you're expressing the flux in terms of temperature and maybe some ambient temperature that I got rid of it by putting a 0. And f of x is the initial temperature. All right, so I remind you that when we work on these problems, we assume some regularity conditions. You can see here there is first derivative of P, so you know P and P prime and Q and I don't know about the source term F. It doesn't look very relevant, but they have to be continuous on the interval that you're solving. And also the conductivity, P has to be positive and R has to be positive. And you can think actually in mathematical grounds where this thing came. They came in when we defined, when we worked out some of the theorems for Sturm-Liouville problems. But in the context of physics, you can think the conductivity has to be positive. You don't want to violate the second law of thermodynamics, okay? So mathematics and thermodynamics actually come together, but it's mathematics here. We don't try to emphasize those things. Okay, so we do separation of variables. We write the solution as capital of X, little x, times some function of temperature. We plug in and you have to trust me, the derivation is trivial, we have done it before. The boundary value problem for capital of X, it's actually the equation that you see here that fits ideally with the Sturm-Liouville boundary value problem, and the boundary conditions for capital of X are what you see on the bottom. But again, I hope I can give you the solutions for the transient problem. So we're going to actually do something about time as well here. All right, so we first have to solve this problem. So this problem has some, discrete eigenvalues lambdas. For each of them, we have shown at least up to now that there are discrete. For each lambda, there is a phi. There are infinite phis. And we wrote a solution in this Fourier-like expansion having some unknown coefficients times the basis functions. And so this was one of our basic theorems. And now, because this is a time-dependent problem, I'm going to make the coefficients to be function of time. Okay? So actually, you can see separation of variables here at work, right? We have separated little x and time. But it's not like we have one function times another function. We have products of functions and then an infinite summation. Okay? All right. I just remind you, in case this has not become clear up to now, the Sturm-Liouville problems really generalize Fourier expansions. In Fourier expansions, you work with sines and cosines. Here, we are actually working with the eigenfunctions of boundary value problems, okay, which can be many different things, okay? And today we will see Bessel functions and Legendre functions, etc. As a matter of fact, if you trivialize this problem, we already have done it, you can actually get sines and cosines. And one of your homework problems, it's actually reproducing from periodic boundary conditions in a boundary value problem, reproducing a Fourier expansion. I think we did it in class, so it's a repetition, but I gave it to you as a homework. Okay, so we need to now compute these coefficients Bn of t. So we assume we solved this problem. We got Bn. We need to find these coefficients. So obviously, we're going to have to put this expansion back to the transient nonlinear heat conduction problem that you see on the top. So you do all the algebra, and the only thing you really need to remember is when you work on this term and this term, you remember this and this term together is minus L operating on U, where L is the operator we use in our eigenvalue problem. So when you do the algebra and you plug in, so here you have U derivative with respect to X. So this is U, right? So that's the derivative. And then you have another derivative with respect to X, okay? So I can move the summation outside. And then inside I have the derivative now of P times phi prime. And then I have minus Q times phi, okay, times B. So if I organize things together, you can immediately see here that this is minus the operator L operating on phi n. And from the eigenvalue problem, this is R times lambda n times phi n. You remember that? For the homogeneous, the Sturm-Liouville problem, L of U is lambda times R times U, all right? So in phi are the eigenfunctions, right? So I have minus R times lambda n phi n, and it's minus R because we had defined L to be minus this operator here, okay? All right. I trust you will revisit this and be sure that you understand it. So if you work on these two terms together, you get minus R times this very nice summation. Here you have Q times U. I'm sorry, Q times U already did it. So let's work on R times time derivative now. R times time derivative. So we put the approximation for U. Right, that's our summation. Actually, it's not an approximation, it's exact, right? I mean, if you have an infinite summation, if you compute every term and you sum them, actually this should converge pointwise to the correct solution. So we plug in this, we have derivatives with respect to t, which means we're going to get bn prime of t. That's the derivative of bn with respect to t. There is no dependence in time in x, in phi of x. All right, so remember, this term involves R times some summation, and this term that we computed is R times some summation. So we will do the same trick we did for the general derivation. We're going to expand this last term in the eigenfunctions phi of x, but instead of expanding directly f, we're going to write f as f divided by R times R. You remember that? Right? And the reason you write it like that is because you want to get rid of this R from all the terms. Right? I didn't hear a yes. That was a weak yes. That was a very weak yes. Yes, all right. Okay. So we're going to expand f over R in phi n. And remember, R is known. The source term f, capital F, is known. So the coefficients gamma n are known. So remember, R and R cancel out. This can be a typical mistake that you do in a homework or in exam, because you're going to say, oh, you know, these are the projections of capital F on the basis functions that always the inner product has R, but here we're projecting F over R. So R and R cancel, so you get capital of F times phi n. All right, so if you put all of these things together and you get rid of R, this is what you get. And as we have done with power series expansions, right, for this to be valid, then this has to be equal to 0, and that's a system, an infinite system of ordinary differential equations for Bn. There is a nice thing here, that these equations are uncoupled. Have you noticed? Because in lots of very interesting problems in engineering and physics, these equations, unfortunately, will be coupled with each other. And that coupling can lead to extremely important phenomena. But here it looks like, you know, things are nice. You know, they work nicely. These equations are not coupled. So B1 is not coupled with B2. All right, so to solve this problem, what do we need? We need an initial condition for Bn. Where do we get the initial condition? We discussed this last time. So we know, so let me write the equation. We know that the initial temperature is equal to f of x. We haven't used that yet. So you remember U is written by this generic expansion. Now I calculate it at time t, right, to make my initial condition. So effectively, the initial condition for little bn can be computed directly. I wrote here Bn of 0. I wrote it as capital B of n, right? So you can calculate this from this expansion. Can you actually give me the formula for Bn now? So before I click go, tell me what's the formula for Bn without looking on your computer. What is the formula for Bn, for capital Bn? So you have f of x equal to this. So each coefficient now, this is like a Fourier expansion in Pn. Tell me what each coefficient then is equal to. Would be an integral, obviously, of what? F of x times Pn of x, yeah? Why are you hesitating? Times R of x. Okay? How does that R comes, right? If you think about it, it comes by taking the inner product of this with the function Pn. But to get rid all the terms but one here, to get the coefficient Bn, you have to use the orthogonality of Pn, and the orthogonality of Pn involves R. Okay? If you miss this, it's not like, oh, can I get 1 point off? 10 points off. Because that's one of the most essential parts of what we do, right? So it's extremely important. So remember this. The TAs will remember that too when they grade it. If I ever see them before the end of the semester. All right, so we can actually solve. We have an initial condition for this problem given by this nice thing. So you can actually solve it. It's a, simple ODE. So you have basically the homogeneous solution, which you know, and then we have done this before. That's a particular solution. And this is, you remember the forcing term that we calculated, right? And is given what you see on the bottom. So, all right, so we got everything. So let me just write the solution. Done. So U of x of t equal the summation of Bn of t times Pn. The Bn is given by this wonderful formula. The capital Bn is given by this. This gamma is given by this formula. We have everything. We're done. We're done, okay? So we took a very complicated transient heat conduction problem with actually conductivity and specific heats, everything, and the sources being functions of x. And even with that complexity, we have an analytical solution. Not bad, right? Okay, one simple example. I'm not going to do all the algebra. I'm just going to give you the final formula. If you have a simple heat conduction where the only source term is x e to the minus t, I have you the general formula here. You know, you can see how this fits in the general category. But what I want to give you is, actually, let me go back. You should be able to recognize that the homogeneous Sturm-Liouville problem is y double prime plus lambda y equal to 0. Why is that? Because if you look at this general problem, right? Actually, let's look at the second equation. P in this case is equal to 1, right? No, I'm sorry. P is equal, we look in UXX. Do you agree that P is equal to 1? Can you see from there that P is equal to 1? Yes, thank you. So R is equal to 1, right, from the first term. I don't see any Q, so Q equal to 0. And the source term, capital F, is x e to the minus t. So the homogeneous Sturm-Liouville problem is that second equation will be P, which is 1. Here, obviously, I missed one derivative, right? So I should go back and correct this. So it's P x prime, and that will give me y double prime, right? Q is 0, and then I have plus lambda times R, which is 1 times y. So the homogeneous problem is y double prime plus lambda y equal to 0. And we already know, it's in the notes, the solutions of that are signs, and here are the eigenfunctions. So if you work the algebra on this problem, you compute all the coefficients, you compute bn's, etc. After 2 slides, the solution to this problem is given by this wonderful expansion. Okay? As I told you, there is a book written in the 60s by Karslow and Jagger that has the solutions to any problem that you can imagine on square domains in 2D and 3D. It's a book like that, every problem in heat conduction, okay? But it's really a boring book. It's like if you need a solution, you can search and find it or derive it on your own in 10 minutes. You don't really need a book like that in 2020, okay? And it's heat conduction, right? So it's not that fun. All right, so you may ask now, if you look at this expansion, right, you can actually say, how many terms do I really need to use to make it to converge? And I am going to remind you, if I can see the formula, lambda n for at least big n's is proportional to n squared. So if you see here, if I split the previous summation in 2 terms, here I have 1 over lambda n squared. So lambda n squared is n fourth. So the first term, the summation has terms like n, 1 over n to the 4th. So it converges very rapidly. I bet if you use 2 terms on this summation, you will get a very good answer. And the second term is even better, because this lambda n squared gives you 1 over n to the 4th. And then on the numerator, you have e to the minus something times t, right? So it converges very fast with time. It drops to 0, basically, okay, with time. So, this series converges very nicely, and you can, if you have to solve it, all right? So let me click to see if there's anything I want to tell you. So you may ask me now, how about if the boundary conditions are non-homogeneous? So if I give you, let's say, that this combination of temperature and flux is equal to 5. So what you need to do is, you need to find a particular solution V that satisfies the non-homogeneous boundary conditions, and then repeat the calculations we did up to now, not for the actual solution U, but for U minus V. So that way, U minus V satisfies homogeneous boundary conditions. You remember we did an example some time ago? Okay, so bottom line is, if you have non-homogeneous boundary conditions, is not a problem. You find some particular solution that takes care of the non-homogeneous boundary conditions, and then solve for W. The only thing you have to be careful is that you have to modify your initial terms, and also, you know, any forced terms you have to account for what carries on from V. Okay. Let me just tell you something interesting, okay? So we took, let's say, nonlinear heat conduction. You defined the Sturm-Liouville problem corresponding to that particular you know, differential equation. We expanded on that, and we solved it. Now, in principle, let's say that computing the eigenfunctions is a very difficult problem, right? I mean, you know, if you have some weird coefficients, etc., you say, you know, I cannot do it by hand. It's a weird problem. Here's what you can do. You don't really have to use the boundary value problem that you have at hand. You can use the eigenfunctions of any other boundary value problem on the same domain. So, for example, you can use, you know, sines or cosines. That's what the Fourier expansion is. The only thing you have to be careful is, if there are essential boundary conditions in either end, you need to be sure that your basis functions that you expand satisfy those essential boundary conditions. So in other ways, you can use the same ideas we have now on expansions on basis functions phi n, even if those functions phi n, they don't come from your real problem, right? It can be anything. Just take care of boundary conditions only. If they satisfy those, you're in business. there is something interesting here. I cannot read. What does it say? Here is interesting. This is now a esoteric thing, but I want to tell you. So you remember when we solved the transient problem and we expanded it, we wrote the solution as some coefficients that they're functions of time times the basis functions. If it happens that you don't use the actual boundary value problem, but you use the basis functions from another boundary value problem, those equations, the ODEs that you will get for these coefficients may be coupled. Because using the actual basis functions from your actual boundary value problem decouples those equations. If you use sines, let's say, or cosines or something else, the equations you will get may be coupled. And if they are coupled, you may be doomed. All right? It will be very difficult to solve them even numerically. So just remember that as a parenthesis. Okay. There is a huge area in mathematics that some of you, if you take the second math course, you may, cannot promise anything, you may hear about this, but you notice we write down the solutions as a summation, a combination of basis functions. There is another approach using what's called Green's functions, where instead of summation, you actually use convolution, you use integrals that involve the basis functions. Okay? And those methods are extremely powerful and provide lots of insights to PD problems, but unfortunately we don't have time, so I'm not going to cover those. So remember, these Green's functions, they look like these Fourier expansions that we're doing. However, they involve integrals, not summation. All right, so now we're going to jump. I said 10 minutes, and it's 11 minutes, not good. Okay, and we're going to discuss about singular problems. So I have to be very selective here on what we do. So let me go to slide 94. Okay, so let's consider a Sturm-Liouville problem that looks like the equation that you have here. So that's the general form, okay? And you notice immediately that this coefficient Q is of the form 1 over x, all right? Which means if the boundary value problem is from 0 to 1, the coefficient Q blows up at x equal to 0. So it's discontinuous. Also, you remember that we said, and we use this in the derivation of the theorems, that the conductivity P there has to be positive, but you notice x is actually equal to 0 at x equal to 0. So effectively, this is what we call a singular Sturm-Liouville problem, all right? And singular in the sense that one or more of the assumptions that we use, the constraints we use for the functions P, Q, and R is not satisfied in one of the, or both of the ends of the domain. So in this case, we have an issue for x equal to 0 for both the function Q and the function P. This becomes infinite at x equals 0. This becomes equal to 0. So we violate two of the constraints. And so this is the Bessel equation, all right, that we will deal today. And you will do this in the homework. And that's the Legendre equation. And you can see immediately, for example, if you solve this in the domain -1 to 1 or 0 to 1, you can see the function P here becomes equal to 0 at the ends. All right? So the conductivity will be 0, and effectively, you have an issue. Now you may say, but that's only one point. Will one point be able to affect everything? Yeah. Because, you know, if a solution blows up, you know, imagine that you're trying to solve something, right? And you try to enforce a boundary condition. It says the function should go to infinity there. Obviously, it's not going to be able to recover later on if it has been at infinity at x equal to 0. So we need to do something to address these problems. Now you may say, are these problems common in engineering? I have bad news for you. These problems are more common than the smooth problems we discussed before. The other problems, you never see them actually in real problems. This is what you see in real problems, okay? So, all right. Let me see now what we're going to do. So let me jump to slide 97. And I'm actually going to do something that I know you guys have done in your homework, in an earlier homework, but you forgot. You remember somewhere I had asked you to solve something with the Bessel functions in the previous homework. So let's say this is our problem, right? It's an eigen value problem. We don't know if it fits in the Sturm-Liouville type of problem, but you can write it like that, and you can see it's actually a singular Sturm-Liouville problem because P of x equal to x is 0 at x equal to 0, all right? So let's try to solve this problem, okay? So the first thing we're going to do is we're going to introduce a new variable, all right? So we're going to change the independent variable from x to t. And I remember, is this what you did in one of the homeworks, a transformation like that? With the Bessel functions, you remember? I was asking to derive the solutions of an equation looking like this. So I told you as a hint to do this transformation. So if you do this, all the derivatives you have here are with respect to x, so you're going to have to use the chain rule, make them derivatives with respect to t. So if you do that, dy over dx be dy over dt, dt over dx, which is square root of lambda. The second derivative, square root of lambda times square root of lambda will give you lambda. If you plug in this in the equation and you write things in terms of the variable t, this is what you get. And this is the Bessel equation of order 0, okay? And, all right? And actually, you can see so this is the general form of the Bessel equation. If this is nu equal to 0, you can see these two terms combined with a different sign, right? They give you, if you put this on the other side, right? They give you this term, and then ty gives you this term there. Okay? So this is a Bessel equation of order 0, and we know how to solve it. And you may say, okay, if you told us that this is a singular, Sturm-Liouville problem, how is the singularity going to come with the Bessel functions that we get? So I remind you there are two fundamental solutions to the Bessel equation. This is of the first kind, and this is of the second kind. And the expressions, so the solution will be a combination of the two. And I'm going back to the original variable x now. The original t square root of lambda times x. And the solutions are looking very complicated. You don't have to remember. Remember some functions like the Bessel functions. They are not known because you memorize this form. They are known because of the equation they solve. Okay? So more interesting equations are the equations that actually look complicated, and they are complicated, but they solve fundamental problems in physics. So the Bessel equations are of those types. So we have a combination of Bessel functions of the first and the second kind. And I only want to plot those, so the rest is not very important. Observe that y0, what does it do at x equal to 0? It blows up. So let's say that I ask you to solve this boundary value problem, and I put for you a boundary condition that says y at 0 equal to 0. Can you tell me what combination of those two functions will give you y at 0 equal to 0? Look at the plots and tell me what combinations of the two Bessel functions will give you y at 0 equal to 0. Can you have y, y, capital Y0, can you have it there in your solution? No, because it goes to infinity. Can you have J0? No, it takes the value 1. So if you try to enforce the boundary condition y at 0 equal to 0, there's no solution. You're doomed. All right? And then the question is, then what type of boundary conditions I'm actually going to put at y equals 0 if I cannot put y at 0 equal to 0? All right? So let me, again, I'm going to do some jumping. And you know what boundary condition I'm going to do is I am only going to say that y at 0 is bounded. I am not going to say anything else. I am not going to say is equal to 1 or 2. I'm going to say it's bounded. So if I say that the combination that I'm going to use of the two functions is bounded, how will that combination look like if I want C1 times J0 and C2 times Y0 to be bounded? What do I need to have for C1 and C2? If one blows up to infinity, how do I combine them for the solution to be bounded? C2 equal to 0. All right, so you're going to have C2 equal to 0. So by saying bounded at x equals 0, the overall solution will be some constant times J0 of x. And then, of course, to compute the eigenvalues and the eigenfunctions, you're going to have to put some boundary conditions, say at x equal to 1. So maybe at x equal to 1, y is equal to 0. So in that case, you are going to have eigenvalues that are defined by the roots of J0 square root of lambda x equal to 0. Okay? And that's exactly what you guys have to do in your homework. And that's the problem I have here. Right? So if I only give you y1 equal to 0 and you only keep this, so you're going to have the to compute the eigenvalues. You're going to have to find the roots of this. And may I ask you actually, maybe during Thanksgiving, just play a little bit with MATLAB on how to use maybe Newton's iterative process to compute the roots of this type of equations. I mean, if you look on Wikipedia and say roots of the Bessel equation, it will give them for you. But if you write a one-line program with Newton's method, you can actually compute them as well. So you don't have to search, right? But you remember if I can go back, there was a plot, I think, right? If you can see here, J0 of x, look how many roots he has. 1, 2, 3, 4, 5, has infinite roots. So there is the formula may not be nice, may not be like the roots are, n squared times this, maybe 3.1, 0.6789. The other one, who knows, maybe 5.37. They're weird numbers, but they're important numbers because they're the roots of the Bessel equation of the first kind. All right. So if you do all of this, and then you are done. Now, there is a fundamental question, and you may have to deal with this in the homework for sure, is if we have a problem like this that is singular, let's say at x equals 0, right? Can we actually expand any function on this eigenfunctions Pn of x? All right? Can we actually use the ideas for non-singular problems and write Fourier expansions in terms of Bessel functions? The answer is yes, actually. If you look at books, people are expanding on Bessel's functions and Legendre polynomials and this and that. They are doing it. But the question is there any theory that somehow allow us to use these expansions that we actually developed only for non-singular problems? Well, let me just put a little bit in a parenthesis here, and I'm going to go directly on what we need, which is on slide 105. The derivation, I'm going to explain what it is nothing fancy. So basically, I'm going to put the whole thing up. The only thing we need to be sure is that the Lagrange identity is satisfied. So to be able to expand on this eigenfunctions of singular boundary value problems, we need to be sure that the Lagrange identity is satisfied. And you remember the Lagrange identity, if your interval is from 0 to 1, is that for any functions that have the right differentiability conditions, L of u times v minus u LV, when you integrate, you get 0. Now, if you have a singular problem, the algebra is not going to come to be 0 exactly. So let me explain what we need to do. When we calculate this integral, let's assume that the singularity is at x equals 0, just for an example. Do you remember when we did integration by parts twice to prove that this is equal to 0? When we did integration by parts, there were a lot of many other terms that we got. You remember those terms? Those terms were from the boundary conditions. And they dropped out. They canceled. So here is what is going to happen. If you have a singularity at x equal to 0, you are going to start with the Lagrange identity trying to prove it. But the Lagrange identity, instead of putting x equal to 0 there, you're going to use a small epsilon. So we're going to do sort of a limit process where instead of integrating from 0 to 1, we're going to integrate from 0 plus to 1, okay? So when you integrate from 0 plus to 1 or from epsilon to 1, the boundary terms that correspond to the left-hand side of the boundary are going to stay there. They are not going to cancel. So the Lagrange identity, instead of being 0, is going to be equal to this limit. You have to trust me. If you put epsilon equal to 0, it looks exactly what we had before for regular boundary value problems. Integration by parts twice will give you these two terms on the left and two similar terms on the right that have canceled out. All right, so the two terms on the left, I leave them there because that epsilon is not 0, is going towards 0, but it's not 0. Is 0 plus, yeah, it's a close number to 0, but on the positive side. So for the Lagrange identity to be equal to 0, and then to actually show that you can expand on the eigenfunctions of the singular Sturm-Liouville problems, this limit, as epsilon goes to 0, has to be equal to 0. All right, the limit has to be equal to 0. And I'm going to give you an example for the Bessel function problem to convince you that actually it comes to be equal to 0. That's why we can expand in Bessel functions. So let me see where I can show you the example. It's on slide 109. All right, so slide 109. So this is our the boundary value problem we worked before. So can somebody look carefully on this boundary value problem and tell me why this is equal to 0? Remember, to solve the Bessel equation, we assume that at x equals 0, the solution is, what was the condition we put on the left? We couldn't put y at 0 equal to 0. We said that the solution on the left is bounded. All right? So effectively, when you try to prove the Lagrange identity, you remember u and v have to satisfy the boundary conditions, so u and v are, have to be bounded. All right? They have to have bounded derivatives as well. And how much is p in this problem? Can you look at this and tell me how much is p? How much is p? No, not 1. What is p here? You remember our differential equation is minus p, y prime, the whole thing prime. So what is p? What is p? X. And how much is x at 0? 0. So as epsilon goes to 0, because this parenthesis is bounded, you multiply by 0, you get 0. All right? And everything falls in place. So even though this problem is singular, actually the Lagrange identity is satisfied. All right? And you can now expand on Bessel functions and do exactly the same things we have done before with projections and et cetera, et cetera. And actually, you know what? I am going to go to slide 112 to give you an expansion that looks like that. Okay, so here is, you remember the solutions we computed, there were these Bessel functions of the first kind. So we can actually expand on these functions. And by the way, orthogonality of the Bessel functions, you notice that nice x there? Where is that x coming? It's not that x. What x is that? Can you see the r is equal to x? Can you see that r is equal to x here? All right? So if you miss that x, you calculate the integral is not going to give you 0. So you can actually take any function that is bounded on the left, 0 on the right, and actually expand it on Bessel functions. Exactly as we have done with regular boundary value problems. And if you ask, and what are the coefficients? Here is the coefficients. Let me just give you the answer. If you multiply on the left with a Bessel function like this, all right? Let's say you multiply this with a coefficient m, okay? So you're going to get the numerator that you see here. But you notice I multiply by x as well. And why do I multiply by x? Because to get Cm, right, to get Cm, I'm going to have to use the orthogonality of the j zeros, okay, and get rid of all the other n's, but only the m term. And the m term is going to be this integral of j0 square of this x dx. I mean, unfortunately, the Bessel functions, looking at this equation, don't seem to be normalized, okay? So you basically are going to have to calculate this integral. Are these complicated? Not really. Actually, if you use, let's say, Mathematica, you can actually do any calculations you want with Bessel functions, Legendre functions, in one line of program. And I will strongly recommend if you download Mathematica to actually try to play with this, you will see it's exactly one line of calculation. All right. 11 at 11, it's always a magic number. So we are going to move to the third subject in a row, which is, actually there is nothing new here, okay? I don't even know if I should do this. Well, let's do it, okay? It's just one example. All right, so the example is actually waves in a two-dimensional circular membrane, all right? And you remember the wave equation? All right, so here the wave equation is written in polar coordinates. The angular dependence has, we got rid of it because there's no angular dependence in this problem. We take the boundary, U is the, imagine if you have a membrane, U is the vertical, you know, the lateral displacement. So on the boundary, at radius r equal to 1, we put 0 displacement, so it's fixed. The initial displacement is f of r, and the velocity initially is equal to 0, right? So I just want to convince you actually that in simple problems, in mechanics, in fluids, in heat transfer, you actually do get Bessel functions, all right? And actually, you know what, something magic? If you take the same problem and you write it in Cartesian coordinates, maybe you get sines. If you write it in polar, you get Bessel functions. And if you write it in spherical, you may get Legendre polynomials. So all of them come to actually represent the same problem in different coordinates. Interesting, okay? So we want to solve this problem, okay? Do separation of variables, right? That's the only thing we know. We don't guess things. So function of r times function of t. We plug things in, and we set this equal to a constant. When you do this in the homework, unfortunately, you're going to have to do the tough work, right? You don't know if this constant is going to be positive, is going to be equal to 0, is going to be negative, so you're going to have to try all cases. And if you're lucky, only one case will work, the other ones will give you 0. But try it, just to convince, you know, that there is no, because sometimes you can have a problem with lambda equal to 0 that gives you an eigenfunction that is not 0. We have done that before, okay? But here we set it equal to minus lambda squared. So the equation for capital R looks like that. The equation for capital T looks like that. What type of solutions capital T has? Can you give me? What type of solutions we will get for capital T? Sine cosines, all right? It's a plus, okay? So we're going to get sines of lambda AT and cosines of lambda AT. And what type of solutions, what type of equation is this one? Actually, if you like, just cancel an R from there. What type of equation is that? Looks like? It's a Bessel equation. It doesn't actually scream at you that I'm a Bessel equation, but if you actually do the transformation that we discussed before, right? So if you change the variable from R to lambda times R, okay, the equation becomes immediately a Bessel equation, okay? And again, the same idea, right? So you have a combination of the Bessel functions of order 0 of the first and second kind. If you want to actually, you remember the second kind Bessel function blows up at R equal to 0. So you're not going to have a membrane that goes to infinity at R equals 0. So this thing drops out. So this is the only thing you have. And because the displacements at R equal to 1 are 0, the eigenvalues of J0 of lambda will be the eigenvalues you are looking. And then you have the eigenfunctions. Bottom line, you know what? The bottom line is the solutions, the fundamental solutions. When did you get this cold? Yesterday, 6 o'clock, you were fine. This guy is going to contaminate me in the front of the room, and I'm going to have a miserable weekend. All right, so let me keep a distance. Okay, he was fine yesterday at 6 o'clock. This is what can happen to you. All right, so the solutions are J0 times sine and J0 times cosine. And if you want the general solution, it looks like that. All right, not bad. All right, so you have in the R coordinates, you have this Bessel function of the first kind. And then on time, you have sines and cosines. And now if you go and apply the initial conditions, I'm just going to give you the answer only. So you know the initial displacement is f of r, and the initial velocity is equal to 0. Will you be able to calculate the coefficient Cn for me? Give me a formula for Cn, fast. Cn will be the integral of what? Of f times what? Times that? Times how much is my R function here? There is no x because everything is in polar coordinates. It's R, okay? Divided by the normalization factor J0 squared times R, okay? Actually, the other coefficients with the Kn, with the sign term here, they actually, you get zeros, okay? And that's the answer, done. All right. So very, very useful type of expansions in Bessel functions. And if you look at textbooks, you will find hundreds of different types of expansions that use this very important equation, very important functions from physics. Okay, so I have a few minutes, and I wanted to philosophize a little bit on why these expansions are so important, right? Why? I mean, what is nice about them? Okay, what is, you know, something nice about them? And because I don't have a lot of time, I see I only have 2 minutes. Let me do the following nice problem, and I'm going to go to slide 138. Okay, slide 138. Let me pose the following problem. You have a function f of x, all right? You have a function f of x, and you have one of these Fourier expansions in some basis functions, phi1 to phi n, but you only keep n terms. So Sn is the partial sum where you keep n terms, and R is the function that comes in the Sturm-Liouville problem from where the basis functions phi are coming, all right? So rather than, you know, saying here is my expansion, and I'm going to keep the n terms, I am saying is I'm going to take some, let me see if the equation is there. Yeah, here's my equation, okay? So I am going to take combination of these functions phi I with some coefficients alpha I, and I want to find the coefficients alpha I that minimize this means, you know, this square error. Do we understand what the problem is, right? So I have basis functions phi, all right, coming from a bounded value problem with a function R there. And I want to find the coefficients alpha, all right? So the summation here is finite from 1 to n And I'm asking what are the best coefficients A1, A2 to AN so that this square error is minimized. Can you guess what the answer is going to come to be? Usually what looks nice is the right answer. So when you try to minimize this error, what are those coefficients going to come to be? So they're going to be exactly the coefficients that you get in the Fourier expansion, which means if you truncate a Fourier expansion in 5 terms, or in 10 terms, or in 20 terms, the coefficients you have up to there are actually minimizing this square error that you see there. They're optimal. So the expansion, it doesn't matter if you use 3 terms, or 4 terms, or 5 terms. Any expansion up to n terms, right, it will be optimal. In what sense? It will be optimal because it minimizes this square error that you see up there, okay? And the derivation actually, if you put Sn equal to this integral, and you take derivatives with respect to the coefficients, actually what the answer is going to come that will not surprise you is that the coefficients are coming to be actually the Fourier coefficients. So not only this Fourier expansion, it's wonderful, right, because you can expand practically anything, but it's optimal in this mean square error sense, right? If you change the error and you use some other function, this will not be true. But in the mean square error, this is actually true. Now, let me just go to slide 142, just to tell you one big important statement, and then we're done, okay? So effectively, if you use n terms with n going to infinity, you can actually approximate, in this mean square sense, any function f of x. All right, so any function f of x, you can approximate it in the mean square error sense, means, you know, the mean square error is minimized, okay? So this is mean because you average the error that you do over x, right, for all x's, but you also weight it with r, okay? So you may ask, what type of functions actually can I get by taking combinations of these eigenfunctions from these boundary value problems? Can I get any function that I can think of? Can I get functions with this discontinuity or that discontinuity? So actually what you can get, if I can only see the name, well, I have an example only. So you can get actually all the functions that they are square integrable in the domain of interest. Okay? These are the L2 functions. All of them, you can actually get them with these Fourier expansions. And you may say, these functions that they're square integrable, do they have to be continuous? No, because you know they can be having jumps, and you remember integral of a jump, well, integral of the jump square, unless it's a delta function, it's finite. An important statement, never, I doubt it, in your graduate studies, you will meet any functions that are, have more weird conditions and smoothness than these L2 functions. So you will never actually meet more complicated functions than L2, the square integrable functions, which means all the functions you will meet are actually can be represented optimally in the mean square sense with these Fourier expansions. So basically, this is as good as it gets, okay, in the mean square sense. This whole thing with the approximation areas, right? This is a huge area in mathematics that goes with the name approximation theory, and it's extremely important to numerical simulations as well, because if I'm going to look to approximate my function f of x with something, with some basis functions, always you are going to have to pose this as an optimization problem. You want to minimize some error, and it comes out if the function that you want to approximate, you approximate it with a summation of some basis functions. The best approximation you can get is the one based on these Fourier expansions. Okay? All right. The notes, I think, are sort of self-explanatory, so please take a good read. Ask me if you have, send me an email if you have any